In this video, we will be introducing the Lewis model, which is a conceptual framework for predicting the number of electrons that a given atom will attempt to acquire. We will later use the Lewis model to predict how things will bond together. The Lewis model can be thought of as a bookkeeping procedure for determining the total number of valence electrons that an atom has and how many additional electrons an atom needs in order to fill its current shell. In the Lewis model, what we do is we write down the chemical symbol and write around it the number of valence electrons that an individual atom has. For example, oxygen. If you write out the electron configuration, you'll find that it is 1s2, 2s2, 2p4, which means that oxygen has 6 electrons in its valence shell. That is the shell that it is currently working on filling the electrons of. It has 2s electrons and it has 4p electrons in that shell. So the way that we would represent it using the Lewis model is write out the atomic symbol for the atom that we're working with, which is oxygen, so that's an O, and draw around it the total number of valence electrons. So in the case of oxygen, it would be 6. They are commonly paired up in 2s because each orbital can hold a maximum of 2. So this represents one orbital, this is another orbital, and then here and here are 2 orbitals that have 1 electron each. The Lewis dot structure, or Lewis structures, depict the structural formula with the number of valence electrons. The Lewis structures focus on the valence electrons because chemical bonding involves the transfer or sharing of valence electrons between 2 or more atoms. Now, while the Lewis model is mainly used to illustrate the covalent bonded molecular compounds, it can also be used to illustrate simple ionic compounds. The Lewis symbols can be used to represent the transfer of electrons from a metal atom, that is the group 1A through group 3A metals, to a nonmetal, resulting in ions that are attracted to each other and therefore bonded via an ionic bond. So for example, potassium, if we write out the electron configuration, it would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. When potassium is trying to form a bond, it transfers one of the electrons from its valence shell to another atom, thereby giving us the cation potassium plus 1. In doing so, it is left with a filled octet and no valence electrons. Because valence electrons are the outermost electrons, they are the ones that are involved in chemical bonding. And for non-transition metals, the orbitals will be made up of s and p orbitals, which, as we saw when we were coming up with our electron configurations, can hold a combined total of 8 electrons, which is our octet. 8 electrons gives you your octet, and that is 2 electrons can be stored in an s orbital, and then 2 electrons can be stored in each one of your p orbitals, and there are 3 p orbitals. So that's a total of 6 electrons being stored in the p, 2 being stored in the s, for a combined total of 8. When atoms bond, they tend to gain, lose, or share electrons to obtain a noble gas configuration. This would be, depending on the particular row, an S2P6 type configuration. So if we are working with the second row, that would be a 2S2, 2P6 configuration. If we're working with the third row, that would be the 3S2, 3P6 configuration for our valence electron shell. Non-metal period 2 elements must obey the octet rule. As we saw when we were dealing with our electron configurations, because the n value is 2, there is no access to the d orbitals. So anything in the second row or second period is hard capped at holding 8 electrons in its outer shell. So anything in the second row, the maximum number of electrons it can have is 8. Atoms in the first row or first period, they only have access to the s orbitals. The s orbitals can only hold 2 electrons, and so atoms in the first period or first row follow what's called a duet rule, since they can only have the one s orbital filled, and the one s orbital can only hold 2 electrons. So if you're working in the first row, the first period of the periodic table, that being hydrogen or helium, you can only ever have 2 electrons. Anything in the second row can hold up to 8 electrons. And then when you're working with the third row or below, there are additional exceptions where sometimes they can violate the octet rule, holding on more electrons. The octet rule itself is a guideline for helping us figure out how things are going to bond. Because it is an oversimplification of the general trends in quantum mechanics, there are going to be exceptions to the rule. However, this does not mean that it is not useful. The octet rule is extremely useful when trying to figure out how things are going to bond together. However, we must be aware that there are some exceptions. Thankfully, those exceptions themselves follow rules that we can use to predict when things might violate the octet rule. So some of the exceptions for the octet rule are things like hydrogen, lithium, beryllium, and boron. When they are trying to get a noble gas-like configuration, the nearest noble gas is helium, and helium can only have 2 electrons. So hydrogen, lithium, beryllium, and boron, when they are bonding with things, tend to try to get a helium-like configuration. Helium, just like hydrogen, can only have 2 valence electrons, which is the duet. So things that the nearest noble gas is helium, they will follow the duet rule as opposed to the octet. This means that lithium will lose 1 valence electron. Hydrogen will tend to share or gain 1 electron, though it commonly loses 1 electron to become an H+, particularly when forming a covalent bond. Beryllium will lose 2 electrons to become beryllium 2+, though it can commonly share its 2 electrons in covalent bonds, resulting in a total of 4 valence electrons. Boron tends to lose 3 electrons to become B3+, though it can also share its 3 electrons in covalent bonds, resulting in a total of 6 valence electrons. So for some of the exceptions like beryllium and boron, why they don't fill an octet or obtain 8 electrons, even when sharing electrons via covalent bonds, is that they don't bring enough electrons. Typically, when you form a bond, it involves the sharing of an electron from each one of the atoms involved in the bond. So because beryllium only has 2 valence electrons, it can commonly only get 4 valence electrons through sharing. It shares 2, and 2 are shared with it for a total of 4. Boron has 3 valence electrons, so it will share 3 to form 3 bonds, giving it a total of 6, right? In each bond, 1 electron comes from each atom, and so if boron is forming a bond with 3 things, it is sharing 3 of its electrons to receive 3 electrons from whatever it is bound to, giving you a total of 6. So boron and beryllium, even when they are forming covalent bonds, do not always fill the octet because they just don't bring enough electrons with them. Atoms in the third row or below have a principal quantum number n that is equal to or greater than 3, depending on which row you are working with. So they then have access to d orbitals. This means that atoms beyond silicon can take on more than 8 electrons, although they generally do not. This is what we call violating the octet rule. At times, there is greater stability in those atoms taking on more than 8 electrons, and they can do so, though it is a violation of the octet rule. The octet rule itself, for anything that is not in the second row, is more of a general guideline than a hard, fast rule. So, looking at our periodic table and deciding where things are likely to follow the octet rule and violate the octet rule, we can first look at our first row, our hydrogen and helium. These two follow the duet rule, as do often lithium, beryllium, and boron, although beryllium and boron do not necessarily have to follow the duet rule, depending on what they are bound to. Things like carbon, nitrogen, oxygen, and fluorine, these four, which make up the vast majority of organic molecules, in addition when they're combined with sometimes hydrogen, will always follow the octet rule. So carbon, nitrogen, oxygen, and fluorine will always attempt to get a filled octet through sharing and forming bonds. Anything from the third row down has access to d orbitals, which means that they can violate the octet rule, though they don't always do so. A lot of the times you'll find that when things like silicon, phosphorus, sulfur, chlorine, bromine, and iodine are making bonds, a lot of the times they will be following the octet rule. Although, because they do have access to d orbitals, they will sometimes violate it.